Okay, good morning, everyone. Let's start. Yeah, so first of all, I'm happy to find some of you have already started homework 1. So yeah, as I just bear with me. Like as I repeatedly emphasize, like if you can start early, it will be much easier and better, and you get much chance to seek for help. I don't rush to the last day, this office hours. That will be very crowded, right? Okay, so let us continue with the computational learning theory. So in last lecture, we introduced the basic concepts in the computational learning theory, and made a few important assumptions. Right? So let us just quickly review those notations. Because these are really fundamentally important, but a little bit abstract. That's why we need to spend a little bit more time to reinforce or refresh our mind. Right? So in general, supervised learning setting, we're gonna define an instance space X, right, which contains all possible instances you're gonna use for training or testing, right? And you're gonna define a output space. And for example, we just do binary classification, then your output space is just 1 minus 1, right? If you're doing regression, then your output space can be continuous, right? And then we introduce an unknown distribution over instance space X. Why? Because we assume that our training instances and test instances are drawn from this unknown data distribution. So this is very important because we have to make such assumption to derive some, to be able to derive some generalization error estimate or bound, something like that. You will see that later. And then we assume that there is some unknown target function from mapping from the instance space X to the label space Y. And this unknown target function comes from a concept class C. So the concept class C just defines the type of the target functions you want to learn. Okay? And meanwhile, we introduce a hypothesis space or hypothesis class big H. So this can be viewed as the range where our learning algorithm want to search over, right? So we expect that our learning algorithm will be guided by the training data to search over the hypothesis space H. Then we find a hypothesis in H, which is also a mapping from X to Y. Right? We hope that our learned hypothesis H is a good approximation to the underlying target function F. Right? That's our basic idea or basic principle. Then we denote the set of training examples by S, and suppose their size is M, right? And the labels of those training examples are labeled by the target function F. Okay? Based upon that, right, given your learned hypothesis H and your unknown data distribution D, which in charge of generating all those instances, right? So you can define the generalization error or the true error, right? So can anyone recall what's the definition of this? What's the generalization error? It's can be more explicit. You say the ground truth function, the function of train, and then what? Okay, that's your explanation. Okay. But how do you measure this degree? Yeah, that's probability, right? Yeah. What you said actually is an estimate. It's not the definition. Right? If I want to know what's the true error, I might just find a bunch of test examples and test my error on that test data, right? But that's not the true error. The true error is defined as the probability, where your prediction made by H disagrees with the prediction made by the ground truth. And because your prediction is based on instance generated by the data distribution D, right? So obviously this probability is also determined by D, right? So this one is a fixed constant. Although it's very hard to get exact value of this constant, but this is fixed, right? Because it's a probability, right? And as we discussed in the last lecture, the true error or the generalization error is practically infeasible to compute, right? So in practice, if you want to learn or want to sense how well your learned hypothesis performs, right, we have to estimate the true error, right? So one commonly used estimate, at least, in theory, is the so-called empirical error, which is also called the training error, right? The error you just mentioned is another way to estimate, right? That is more useful in practical applications. And in practice, where it's always like, okay, I train my model on a big training data set, then I test it on a separate held out data set, and I use that accuracy or error, as approximation to the generalization error. Right? That's a practical. Right? But in theory, in theoretical analysis, we're more interested to look at, okay, how well your learned model fit the training data, right? If you learn a hypothesis H, right, and then you use H to predict the labels of all the training examples, and you're gonna say, okay, what's your training error? This is defined as empirical error. So the idea, many research topics in computational learning theory is to use this empirical error to approximate or to bound the generalization error. And you see that like a lot of learning algorithms also motivated by such bound. This is called generalization bound, generalization error bound. Okay, so now I want to ask, right, is empirical error also fixed constant? No, why? We know the true error is a fixed constant, right? It's determined by the distribution D, which is unknown yet exists, right? But what about empirical error? All the training error, is it also a constant? Yeah, this is kind of the same stuff, intuitive, right? But it is based on the training data set, right? So then the problem becomes, we know that the training error or the empirical error is computed based on the training set, right? If it's fixed and constant, does it mean like our training data set is also fixed and constant? No, right? Yes, right. This is the key observation. Right? So our training set actually is a random variable. Why? Because we assume that the training set is sampled from this unknown data distribution D, right? So you can imagine like this time I collect 100 training examples. They're random samples of the data distribution D, right? Next time I collect another 100 examples, is very unlikely that they're going to be the exact same as the 100 examples in my previous trial. Right? That's the key observation. So in essence, the empirical error or the training error is a random variable. It's not some fixed constant stuff, right? Because your empirical error can vary along with the training data. And the training data itself is randomly generated from D. That's the key observation. That's why when we say, okay, if I use empirical error to make some bound or estimate of true error, and this bound must be some function of this training error. I mean, this bound or approximation or estimate, they are running variable as well. That's why we can only say, okay, with how much probability this bound is blah, 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 blah. It's probability statement. You may make assumption about the true error? No. So we're talking about like very general case. Like we're just assuming, okay, it comes from some distribution, some valid distribution. That's it. But of course, if you want more specific results, I might make a further assumption about the properties of D. That is feasible, right? But in our class, we're gonna only talk about very general case. Of course, the theory will seems like simple, but it really reflects important insights. Any other ideas or questions? Okay, great. So then we talk about a very important concept called probably approximate correctness, right? So it is based on our realistic expectation about how well your machine learning algorithm works, right? So why? Because first, you cannot expect a learner to learn a concept exactly because your training data is finite. Right? You can imagine this is a bunch of, let me draw it to be more intuitive. Like your training set, if we represent as those dots, right, or those circles, right, they're finite, right? So your learning essentially is to find a bunch of hypotheses, find a hypothesis which will fit those circles, right? Right. However, because this is a finite number of observations, naturally you can find many hypotheses or functions which perfect fit this finite number of observations. And then which one is the best? Right? Which one is best? No one guarantees, right? We can follow, say, Occam's reasons principle, which we're going to discuss later, right? But even that won't guarantee you that your target function will be the one you choose, right? So you'll never be able to guarantee to find a exact concept, right? Exactly find the concept. It's infeasible, right? And then if we step back and can we expect to learn close approximation to a target concept? And this is infeasible as well because the learning is also determined by the quality of the training data, right? So if you got a high quality training data set, which kind of like very good representation of the whole instance space and reflects all the properties of data distribution did, yeah, it might be possible to get a good approximation to a close approximation to a target concept, right? But as we just discussed, the training data is random, and this time you get a very good quality training set, right? Next time you might just have a bad quality training set, right? Which can end up with a very bad hypothesis, which is quite far away from the ground truth. Right? So that means we can not always expect to learn a close approximation to the target concept either. The realistic expectation will be some kind of probability statement. Right? If we could claim that some learner can using high probability, can with high probability find a close approximation to the target concept, then we're successful. That's the basic idea. And based on that idea, we introduce this probability approximate correctness, which can be viewed as a criterion to differentiate those efficient learners and inefficient learners. Okay. Does it make sense? Everyone is good so far? Okay. No, just trying to review those concepts and to make sure that everyone is comfortable with that, right? Because this is a little bit abstract, right? So what is probably approximate correctness, PAC, right? So we first introduce two parameters. epsilon and delta, right? So epsilon indicates the level of your true error, right? And delta indicates your probability, the level of your probability statement. As we mentioned, like a realistic expectation about a good learner is that, okay, with high probability, your true error, your learned hypothesis has true error, has low true error, right? So, and then if you want to quantify this, right? If you want to give a more rigorous, more clear description, I'm going to specify what is your error level, right? What is your confidence level, right? And then given any instantiation of epsilon and delta, we can claim, okay, something about the learner's performance, that is, with probability at least 1 minus delta, your learner can produce a hypothesis with true error at most epsilon. Right? This can be some kind of pretty accurate and specific description about the performance of your learner. Like, for example, if I take epsilon to be 0.05 and delta to be 0.05, right? So then our description of your learner will be, okay, your learner can, with probability at least 0.95, right? To find a hypothesis with true error at most 0.05, right? So that means it reflects your learner is pretty good. And now we can define the concept of pack learnability, right? So pack learnability is way more strong, way stronger than this, right? So we consider a concept class C, meaning the type of or family of target functions we want to learn, right? Which is a mapping from the instance space X to some output space Y, right? And we assume that your instance is represented by a feature vector of length n, right? Your learner is denoted by L, right? And the hypothesis space H is where your learner L will search over, right? Then we see that the concept class C is pack learnable by L using hypothesis space H if, right, for every possible target function in your family C, right? For every possible distribution D over the instance space, and for every possible choice of your error level and confidence level, your learner only need a polynomial order of examples to achieve the corresponding performance statement. Namely, it can with probability at least 1 minus delta to find a hypothesis H from the space that has true error at most epsilon. Right? And probably a polynomial order more specific means that it is the number of training examples is polynomial in 1 over your error level, epsilon, 1 over delta, the confidence level, and the size, the length of input vectors, and the size of hypothesis space. So basically what that means if your L can pack learn this type of target functions, that means L don't use too many training examples. It just use a polynomial many training examples can achieve the any probabilistic statement of its performance. So that actually defines what learning algorithms is efficient. Right? Its efficiency is reflected by the number of training examples it used. Right? You just use a polynomial number of examples to the properties of the performance you want. Right? That's very good. Right? Imagine that if your learning algorithm, if you want to achieve the performance, like same performance, like that means with at least 1 minus delta, and to get a hypothesis with true error at most epsilon, but the number of training examples required is exponential to those factors. That will be too expensive, right? It needs too many examples. In other words, your training example, your learning algorithm might not be efficient enough to leverage the training information. Does it make sense? So it just means if you can write down a m, right, the skew of m can be viewed as polynomial function of those four factors. Right? It's very similar to, it's actually the same definition of like time complexity, space complexity in your data structure course. Yeah, epsilon and delta comes from you, right? You designate what is the error level and delta level you want, right? Of course, the smaller epsilon, smaller delta means that okay, you got like higher requirement about the performance, right? Of course, the number of training examples will vary as well, right? Because different requirements will require different number of training examples. It's like if you want different service, you're gonna pay different price, right? And n comes from your instance space, right? Your defined instance space. How many features do you need to represent each instance, right? That's n. And size of h actually indicates the size of hypothesis space, right? And reflects the complexity of your algorithm. Right? So you can imagine the larger the hypothesis space, that means you're going to search over the larger range. So that means your machine learning model is more complex. There's no roots. So you can imagine like what is polynomial? If I say m as a function of these guys, so it means m is a polynomial functions of these four factors. So let me just write down some polynomial. See, if it's a function of x1, x2, it just means okay, it might be a times x1 squared plus b times x2 cubic, times c x1, x2, something like that. It's just polynomial function. I shouldn't contain like exponential of x1 or sine x2, something like that. Any other question? Instance space, just the space of input vectors. Like for example, if you convert or represent your training examples by an n-dimensional feature vector, right? If your feature vector, say, is n-dimensional and is a continuous value, then you can define your feature space by r to the power of n, right? And of course, if you have some range of the value of the feature each one you use, for example, if you just use binary features, and then your instance space will be -1, 1 to the power of n, right? It up to how you're gonna choose your feature vector representations, right? Another question? Okay, great. So the key idea, I mean, this is a very lengthy definition, but the key idea is pretty simple. It just tell you, okay, if some learner algorithm, which can use not too many examples, like just polynomial to some to the factors which decides your performance to achieve that performance, then your learner is considered to be efficient, and your learner it can pack learn the concept class. Right? But if you want this language to be precise, well, we have to use those long sentences, right? So if you're uncomfortable, just read this sentence for 5 times. You get used to that. Okay, so here, I'm to emphasize again, right? Epsilon delta, right? So it means the pack learnability requires that for arbitrary epsilon delta, right? So it means you you can designate any generalization error level and any confidence level, right? And then you can, and then the number of training examples is polynomial to them, and you can achieve that performance described by epsilon delta. If someone may ask, okay, this is a talk about the sample complexity, right? The number of samples you're going to use to achieve some designated performance. But from computer science perspective, we also need to look at if the algorithm can be efficiently run, right? So then we can add additional definition, right? So if we further say, if further the learner L can produce the hypothesis in time complexity is also polynomial in these 4 factors, then we say the concept class C is efficiently learnable. Right? It just means, okay, I not only just use a polynomial many number of training examples, but also my time complexity is polynomial to these 4 factors. Does it make sense? Okay. So now we can extract some insight from the definition of packed learnability, right? So packed learnability imposes 2 requirements. First, polynomial sample complexity. So why do we need polynomial sample complexity? We just want our algorithm to efficiently leverage the information inside examples, right? I don't want too many examples. If I want to increase the performance a little bit, then the increase of training examples tends to be huge, right? Tend to grow exponentially. This is not something we want, right? This is not realistic in practice, right? So we require you only need a polynomial growth of those examples, and this is more practical, right? And also polynomial time complexity. This is from the computation procedure, right? Or searching procedure. If your searching procedure only takes polynomial time complexity, that is viewed as good. Right? So we know that in our algorithm design class or data structure class, polynomial time complexity and space complexity are usually viewed as practically feasible and efficient solutions. And another important concept insight is that if we really want your type of target functions C pack learnable by your algorithm L, right? And then for every possible target function, we must be able to find a hypothesis which has arbitrary small error rate, right? Because pack learnability is a very strong statement. It requires that, okay, for arbitrary error level epsilon, right? Arbitrary confidence level, you can always use a polynomial many number of examples to find a hypothesis whose true error is less than epsilon, right? So that basically means, okay, if you want your hypothesis, your target function to be pack learnable, right? Then for every possible target function, you can find a hypothesis to be arbitrarily close. Then that implies your hypothesis space is a superset of the target functions. Okay. Correctness means that you can exactly recover the concept C, right? But do we correctly or exactly recover that? It's not possible, right? So that's why our claim is described along with this error level, right? So we're saying, okay, epsilon, we can pick arbitrary epsilon, right? That means I can get arbitrarily close to the target function, but I'll never say, okay, we can exactly recover the target function. That's in the limit, right? That's the limit. Limit means, okay, if you make your number of training examples to go to infinity, well, you can converge. You might find a hypothesis to convert to the target function, right? But in practice, you'll never reach the limit. That's why we see approximate correctly, right? And then probability correctness means that our statement is a probability statement, right? It's not deterministic statement. We some high probability saying that, okay, we can find this hypothesis which is epsilon close to the target function, right? And it's high probability, but that doesn't mean you must be able to do that. That's how this term is from. Okay, so let's go back to this point, right? So because the PAC learnability requires that, okay, for any designated error level, right, as long as you provide enough training examples, you're gonna find a hypothesis whose true error is less than epsilon, right? So basically means for arbitrary epsilon, you're gonna have some hypothesis in your hypothesis space which close to F, no more than epsilon. So this basically implies that your hypothesis space must contain a concept class. Otherwise, imagine that, okay, suppose your hypothesis space, right? And there's some target function which is outside this hypothesis space. What will happen? What will happen? That means no matter how smartly you will search over the entire hypothesis space, right? The best one always has some gap, right? And if you can pick up some epsilon less than this gap, and you will never be able to find a hypothesis which is closer to the its distance or its performance gap to the true function is less than this gap, right? So it won't be PAC learnable. So actually, it implies that your hypothesis space must be large enough such that every target function is contained inside. Mm-hmm.
So you said earlier that you have right? So because I would assume that the target of the always got hypothesis space.
No, even you got a very large hypothesis space where your target function inside that will be guaranteed that you will find it, right? So imagine like even I put a small range 0 to 1, there are infinite uncountable numbers on that, right? And it's possible that no matter how smart you are, you cannot locate one particular position. No. Mm-hmm. Yeah, this is how they define it. Yeah. You can invent other languages. I'm just talking about the standard language. Yeah. Yes. Yeah, this is like this epsilon delta, right? It's very similar to epsilon language when you talk about the definition of limit. If you take calculus 1, right, the very first important concept is called limit, right? What does limit mean? It's a lengthy paragraph, right? To introduce that. Okay, I can't forget. Like for arbitrary, for some I think it's B epsilon, right? So for any point, like if you take a neighbor region who's you can view it as a sphere and its radius less than epsilon, and you can find out if we talk about sequence of limit, right? You can find out a subsequence after some step. All the points are inside this small sphere, right? And if that statement holds for arbitrary epsilon, and that means your limit will be the center point, right? This is a very lengthy statement, right? But it precisely or exactly or rigorously defines what what does it mean for limit? Right? So here is same thing. Right? So if you want to give some kind of precise, rigorous definition, what do we mean by efficient learner? We have to use this epsilon delta language. No, it's not. There's no guarantee on that. We're just saying we're going to use epsilon delta language to describe the performance of a learner, right? It's not say, okay, the true mean or the true error is a limit of blah blah blah, right? But later we'll see that we'll see some results that when you increase number of training examples, and then your empirical error will converge to the true error, right? That's some statistical conclusion there. Okay, so now from the definition, we can see that pack learnability essentially is the worst case definition, right? Because it requires that the algorithm must meet its accuracy, right? Designated by epsilon delta for every possible data distribution, right? And for every target function in the class C, right? It's a very strong requirement. Okay, any questions so far about the understanding of this concept? Yeah, I mean, technically speaking, yes, but when they prove this, they're going to use tricks, right? They won't really enumerate every possible function in your target concept, target class, right? But this is just definition. Okay, great. So now, next we're going to talk about how do we use those definitions about true error and empirical error to justify the Occam's razor principle. So we will mention that a bit, right, in our discussion of decision trees, right? We said that, okay, the ideal case should be I'm going to pick up the smallest tree which can well fit data, right? If for the same data set, I got 10 trees, each tree can exactly fit the training data, right? Which one would we choose? We would like to choose the smallest tree, right? I said this is a principle, it's the very prevalent choices, model choices philosophy, but then why, right? So here we're going to give some justification from the perspective of computational learning theory. So first, let us give a more formal definition of Occam's razor principle. So it is named after William of Occam, right? It's many years ago. It just says some philosophical principle that we're going to prefer simpler explanations over more complex ones, right? In other words, right, never posit plurality without necessity, right? So we increase model complexity only when we have to. Right? If we don't have to, don't increase the model complexity. That's the idea of the Occam's razor principle. So historically, this is a widely prevalent idea across different schools of philosophy, right? Religion, philosophy, this kind of stuff, right? But now it has been widely applied to engineering and scientific research. So how are we gonna justify this, right? Let us start with some claim, right? Our claim is as follows. Suppose you got a powerful learner like decision tree. That learner will always guarantee you 0 training error or 0 empirical error. So that means, okay, suppose I give M training examples to my learner, right? I can always find a hypothesis whose prediction is consistent with all M training examples, right? Then, as we mentioned, right, training error, small training error does not imply small generalization error, right? Then we're interested to know, like, what if I find a hypothesis with zero training error, but performs badly in generalization? We want to know how likely this will happen. This is not something we want, right? So we want to characterize the chance this bad thing to happen, right? So our claim is about a bound of the probability of this bad thing. Right? So let's read the claim, right? So the claim is that the probability there is a hypothesis H in your hypothesis space that first, your H is consistent with M training examples, meaning that zero training error, yet the generalization error is bigger than epsilon. Right? This probability is upper bounded by this guy. This is upper bounded by the size of hypothesis space times 1 minus epsilon to the power n. Is everyone clear about the meaning of this claim? Right. So here we use epsilon as some kind of threshold defining whether your learned model performs better, right? So suppose epsilon is given, right? Then I claim that, okay, even I can find a hypothesis such that on all M training examples, its error is zero, right? But its generalization error is still going to be bigger than my threshold epsilon, right? And this probability is less than size of H times 1 minus epsilon to the power of n. This will give you some upper bound of this bad event to happen. Does it make sense? Right. Okay. So basically, it tells you, okay, you find a hypothesis. It's consistent with the training data, yet generalized badly, right? And why we will this as a random event? The reason is because your training data, the M examples are random. So imagine like your training procedure is that, okay, I'm gonna feed my M randomly generate examples to my training examples, to my learning algorithm, and guided by this training set, I'm gonna search for some hypothesis, right? So obviously for some training set, okay, it can make me find a hypothesis whose generalization error is small, is less than epsilon. Some of them, some training set will kind of leave my learning inferior, right? It's kind of find some hypothesis which true error is bigger than epsilon, right? So this is a random event. Right? So the probability of this random event we claim to be less than this guy. I want to make sure everyone is comfortable with this statement. No question? What? I mean, if you feel confused, I mean, that's mostly because you feel uncomfortable about such kind of statement. But the key idea is that this claim wants to give you some characterization. Like you have a perfect learner, meaning that you always find a hypothesis with zero training error. Unfortunately, the hypothesis doesn't generalize well. What's the probability of that? Okay. It's possible, right? Because your performance not only depends on your training algorithm itself, but also depends on the quality of the training data. Right? Training data is random. Right? So you can see training data 1, well, you get zero training error, you find a hypothesis. It performs well as in the generalization case, right? But for training data 2, it gives you a hypothesis. The training error is still 0, but the generation performance is bad. This is a random event. It depends on the training set. That's why it's a random event. Yeah, no problem.
And there's very no chance that it's hypothesis and people that as so I don't know and the friends that very going to be pressure on
Mhm.
and also the consistent this consistent
Yes.
this really consistent.
Yeah, consistent with every segment means that, okay, if you use your H to predict the label of these M examples, they're all correct. Yeah, that means zero training error. Yeah. No. Examples are not in that space. Hypothesis space means all the candidate functions. Right? You want to pick up one candidate function as your learned result. Right? This big H? The big H is the hypothesis space, right? It's all possible functions you're going to search in your learning algorithm. So the learning, as we emphasized, right, is a searching procedure inside this hypothesis space. You're going to pick up the one hypothesis which you believe best as your learned function, right? And usually the best means that, okay, it best fits the training data. But it's possible that, okay, you pick up a hypothesis, right, which perfect fit all the M training examples, but its true error or generalization error is still large. The H corresponds to what? No, it's a function space. So suppose you are learning your model is a linear model, right? So your model can be represented as W transpose X equals to 0, right? So the hypothesis space contains all such linear functions. You're going to pick out one function which you believe is best and is close to the target function. This H, this means the size of hypothesis space. Yeah, the number of the candidate functions inside the hypothesis space. Yeah. And this means 1 minus epsilon to the power of M. So someone asks, okay, you ask, it can be very small, right? But at the same time, it also depends on the size of hypothesis space. Right? If hypothesis space is very large, then it can still be big, right? Yeah. Yeah, in some cases, like your H space can be very large. In some cases, like H can be small, right? It depends on what learning algorithm you're going to choose. Right? If you use, I don't know, if you use decision trees, if you use fully growing decision trees, the hypothesis space may contain all possible trees, right? If you fix your decision tree to be depth 1, right, only grow 1 tree, right? Your hypothesis space is much smaller, right? It depends your choice. Another question? I mean, if you feel uncomfortable, again, read through this multiple times. Right? But the idea is like that. Right? The key idea which we want to deliver is that even you can find a hypothesis with perfectly fitting to the training set, it doesn't mean you got good generalization error, right? It can have some bad generalization error. Then, and this depends on the training set, right? Because the training set is random. It randomly drawn from data distribution D. So different set of training examples may lead to different learned hypotheses, then leads to different generalization error, right? And here our statement is to give you an upper bound of such things, right? The upper bound that you find a hypothesis with a 0 training error, but the generalization error is still bigger than epsilon. So let's try to prove this to strengthen our understanding. You see that the proof only requires some basic knowledge about probabilities and inequalities, which you have done for homework 0. So first, let us consider the case, right? Let us do not consider the existence statement, right? Here is the existence statement, mean that there exists something, right? So here, let us assume H is there, right? We have some particular H in our hand, right? H, we know is a bad hypothesis, right? And its true error is bigger than epsilon, right? Then we'll want to say, what's the probability that it also can consistently predict M examples, right? Because H has true error bigger than epsilon, right? Then it make correct prediction for one example, this probability will be less than 1 minus epsilon, right? Does it make sense? Right? So now, because we're assuming that all those M training examples are drawn independently from the data distribution D, right? So that means your H can perfectly predict the labels of all M examples will be less than 1 minus epsilon to the power of M, right? So basically it says the very first conclusion we can get is that H is bad, yet consistent with all M training examples. This probability is less than 1 minus epsilon to the power of M, right? Okay, but this is not enough, right? Because right now we just characterize the probability that you're given a hypothesis, right? A particular hypothesis we know is bad, and then it still can correctly predict M training examples. This probability is upper bounded by 1 minus epsilon to the power of M, right? So our question is that what is such a probability for the existent statement? So what is the probability that there exists some bad hypothesis in H that is consistent with all M examples? So look, so we can see the difference here, right? So first statement tells that, okay, if H is in our hand, right, what's the probability that, okay, it is consistent with M examples, right? A second problem is that, okay, we want to talk about what is probability that there exists some bad hypothesis who can correctly predict labels for the M training examples. H is bad here. A means its true error is bigger than epsilon. So to give this proof, right? To bound the probability about their existence of such a bad event, right? We can consider decompose this event, right? So let us define event A. Event A says there exists some bad hypothesis, meaning that there exists some hypothesis whose true error is less than epsilon, right? Is bigger than epsilon, right? There exists some bad hypothesis in big H, yet is consistent with M training examples. So we want to know what's the upper bound of the probability of event A, right? That's our goal, right? And then we can decompose this event by a union of a set of individual events, right? Remember, this is what we have reviewed in homework 0, right? So even A can be represented by a set of events. That is, the first hypothesis in H is bad, yet consistent with M examples. Or the second hypothesis in the hypothesis space is bad, yet consistent with M examples. Or blah, blah, blah. Or the last hypothesis is bad, yet consistent with M examples, right? So you can see it's just a simple union of a bunch of individual events, right? And then we can upper bound the probability of a union of a set of events by the summation of the probability of each individual events, right? So because A is union of B1, B2, B3 until B size of hypothesis space H, right? So the probability of A will upper bounded by P of B1 plus P of B2 plus P of B3 and blah, 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 right? And then what is probability of each B? Any thought? Yeah, this is something we have just analyzed, right? For any particular hypothesis, it's bad yet consistent with M examples. This probability is upper bounded by 1 minus epsilon M, right? So actually, every B event is talking about that, right? So its probability, each of these P, B1, B2, and so on, is upper bounded by this 1 minus epsilon to the power of M, right? So the total bound will be the size of hypothesis space H times 1 minus epsilon to M, right? That's how we derive this result. Right? I mean, this proof is not hard at all, right? And I believe everyone can do that, right? But I just want everyone to walk through this proof or even write down the proof by yourself if you feel uncomfortable in reading the statement. Right? Once you can prove that, you will feel much more comfortable looking at this statement. Okay. Based on this statement, what can we conclude? What can we observe? So now we know that, okay, even you have a powerful learning algorithm like decision tree, and even you can find a hypothesis who can correctly predict all your training examples, but you still have a chance that your learned hypothesis perform badly in the generalization, right? So the chance is upper bounded by size of H times 1 minus epsilon to M, okay? So obviously, I don't want this to happen, right? I don't want this bad event to happen. I want to control this probability, right? I want to look at satisfying what kind of conditions should we do to make or to squeeze this bad events probability to be smaller than, say, delta. Right? Suppose I happen to find a consistent hypothesis with true error bigger than epsilon, this chance to be less than 0.05, right? I want to look at what can I do to achieve that, right? So let us try to do that, right? Suppose I want to make this probability to be small, say smaller than some given threshold delta, right? That means as long as we can make is the upper bound of this probability to be less than delta, right? Then we can try to solve this inequality in terms of the size of training data set, M, right? And then we can know, okay, how many examples do I need to decrease or control my bad event to happen, to control the probability of my bad event happen to be less than delta, right? So then we can just solve the inequality, right? So here we take logarithm on both sides, right? Log size of hypothesis H plus M times logarithm 1 minus epsilon less than this log delta, right? And here we're gonna use some known inequality, that is logarithm 1 minus delta if further is less than minus logarithm 1 minus epsilon less than minus epsilon. So just to substitute into that, you get this guy, right? Logarithm plus H plus M logarithm 1 minus epsilon less than logarithm H plus M times minus epsilon. Now I further solve this upper bound less than logarithm delta, and then do some simple algebraic operations, you can get that when your number of examples is bigger than this guy, then the probability of getting a bad yet consistent hypothesis is small. How small is this probability will be less than delta. Right? That's the idea, right? So by solving this probability, by solving this inequality, we can see that, okay, if your number of training examples is bigger than this lower bound, right? It's bigger than 1 over epsilon logarithm size of h plus logarithm 1 minus delta, then I guarantee that the probability you find a hypothesis which has 0 training error, yet the true error is bigger than epsilon, is less than your designated delta. So now let us look at what does this bound of the number of examples can reflect. Right? So to reinforce our understanding, I want to rephrase this again. Right? Let big H to be any hypothesis space, right? Suppose you got a powerful learning algorithm like decision tree, which guarantees no matter what training example, what training data set you present to your algorithm, you always find a consistent hypothesis. Consistent hypothesis means that your training error is always 0.
So this requires you to
That's a very good point. That's a very good point. We're going to discuss about that later, right? So let us just assume your hypothesis space is finite. Okay, any other questions before I? Okay. So if your number of training examples or training data sets size is bigger than this lower bound, then we claim that with probability at least 1 minus delta, your hypothesis, your learned hypothesis will have true error less than epsilon. Okay. So now what does this bound mean, right? So because this is a bound about the size of training data, so it's called sample complexity bound. Right? It's a lower bound, right? Sample complexity bound, right? So want to look at like what does the lower bound reflect, right? What kind of insights can we extract from this lower bound, right? So first, if you want to expect a lower generalization error, say, if you want to decrease epsilon, right? What will happen? You're going to increase the whole sample complexity bound, right? That means if you want to lower generalization error, you have to use more training examples. This is very reasonable, right? No pain, no gains, right? If you want to get better performance, of course, you need more training data. Right? And the second thing is even more interesting. Right? Suppose you got two hypothesis spaces, right? H1, H2, right? And given the same epsilon delta level, using which hypothesis space will give you a larger sample complexity bound. Right? So let me state again, right? Suppose you consider two hypothesis spaces, right? So suppose the first hypothesis space is bigger than the second hypothesis space. So now given the same epsilon delta, right? So suppose I expect my generalization error to be epsilon and the probability level to be delta, right? For both cases, for both hypothesis spaces, right? Now, using which hypothesis space will lead to larger sample complexity bound? H1, right? You can see that this one is proportional to the logarithm of size hypothesis space, right? That means, okay, the larger the hypothesis space used, the more training examples you will need to achieve the same generalization error under the same probability, right? This actually reflects or justifies the Occam's razor's principle. So what does Occam's razor's principle tell us, right? If you can equally well explain, if you got several models, right, can equally explain data, right? And then you're gonna pick up the smaller or simpler one, right? And here, the hypothesis space reflects the complexity of your model. So to achieve the same performance, epsilon and delta, right? The smaller hypothesis you use means that the simpler the model you use, the smaller training examples you will need. And that means you will save more cost, right? That's why we favor simpler models. So this kind of like justifies why we would like to use simpler models. Right? But of course, if your models are too simple, that means for some hypothesis space, like you might never be able to reach the same epsilon delta level. And of course, but it's not like here we assume that epsilon delta are the same. Yeah, that's your model choice, right? Right now we talk about decision trees. We're actually assuming our hypothesis space are finite, right? Because all your features must be discrete, right? And your size of tree is upper bounded with regarding to the number of features, that kind of stuff, right? The hypothesis space is finite, right? But as we mentioned, right, when we want to restrict the tree size, you can still choose. That corresponds to the choosing a hypothesis space, right? For example, if I restrict my tree's depth to be 1, to be 2, to be 3, I have to choose different lists, a different set of hypothesis spaces, right? Yeah. That's a good point. So basically, today we're going to discuss, like we give the full proof is about the case that hypothesis space is finite, right? But in many cases, hypothesis space is infinite, right? And then that sample complexity bound won't work. And then we'll talk about another sample complexity bound, which is defined on a different measure, right? You can measure the complexity of a hypothesis space, even it's infinite. It's called VC dimension. And in computational learning theory, they also have derived the sample complexity bound for infinite hypothesis space. Linear, yeah, exactly right. Even for the linear regression model or linear classifiers, the hypothesis space is infinite. Why? Because your weights of your features are continuous, right? You're gonna have like infinite, many possible candidate functions or hypotheses, right? In that case, this sample complexity bound won't work, right? It cannot characterize the relationship like regarding between generalization performance, the complexity of your model, and your number of examples, right? However, later, after we go through the basic linear regression, the linear classifiers, we're gonna go back to this topic again. Then we're gonna introduce the idea of how we're gonna measure the complexity or capacity of our hypothesis space, even it contains infinite number of members, right? And then we'll give the sample complexity bound in that case, right? You see that by analyzing the sample complexity bound in that case, we can drive a new learning principle, which we call maximizing the margin. Right? When we maximize the margin, we can derive the so-called support definitions. But here, this is mainly a pedagogical example, and showing that the basic concept about computational learning theory, and based upon those simple facts, how can derive the result and reflecting some important insights. Any other question? Okay. Yeah, the last one is about the confidence level or probability level, right? So you can see that the smaller the delta you have, also the larger the sample complexity bound, right? So the smaller the delta have means that, okay, you want your probability that you find a good hypothesis with smaller training error to be as high as possible, right? That means you also need to increase the number of training examples, right? That's very fair, right? Again, there's no free lunch, right? If you want to improve the performance, not only in terms of true error, but also in terms of the chance, right? You have to use more examples. Okay. So, but here, the middle term inside here reflects Occam's razor principle, right? If your algorithm, your two hypothesis choices can give you the chance that same level of epsilon and delta and epsilon, then using a smaller hypothesis space can decrease the number of training examples you want, right? And if you can decrease the number of training examples, you kind of save your cost. Okay. So now we come to the question, right? So I think you guys have asked, what if your hypothesis space is infinite, right? And if your hypothesis is infinite, all the proof previously you have gone through won't work, right? Because remember, when we prove this, right? We decompose this event as a union of a finite number of sub-events, right? However, if your event is decomposed by an infinite union, then if you do the summation over that, the size is infinity, right? So you got infinite bound, right? Infinite bound doesn't mean anything, right? Because any probability is less than infinity. So that won't give you some reasonable sample complexity bound or further insights, right? So basically, the result we have found so far tells us that complicated or larger hypothesis spaces are not necessarily bad, but simpler ones are unlikely to fool us by being consistent with many examples. Meaning that, okay, if you got simpler hypothesis space, which you can also give very small training error, like zero training error, then we should go for that. Okay? We shouldn't use a larger one, because for the larger space, you're more likely to find those weird functions which can also fit training data well, but performs better. Right? That's the intuition. Okay, so I think that's all we need to discuss today, right? We're gonna stop earlier today, right? See you on next Tuesday.